what is a Delaunay triangulation? We'll start by defining what a Delaunay graph is, and for that we have to go back to the notion of Voronoi diagrams. So let's say I have a point set and I have the Voronoi diagram of that point set. The Delaunay graph is now the dual graph of that Voronoi diagram. So what does that mean? For every cell of the Voronoi diagram, I want to have a vertex in the Delaunay graph. The cells of the Voronoi diagram correspond to the input points. So that means as vertices of the Delaunay graph, I will have simply the set P. And now I want to have an edge between 2 points if the 2 cells are adjacent, by which we here mean they share an edge. And that's then the dual graph of the Voronoi diagram, and it's called not quite Delaunay graph yet, because the Delaunay graph is now the straight line drawing of that graph. So where between any 2 points I take the straight edge. Here, for instance, these 2 points, they correspond to these 2 cells. Those cells share an edge, so the Delaunay graph has an edge, and it has simply as edge the segment between those 2 points. That is a Delaunay graph, and let's have a look at more properties of this graph. In particular, we want to show that it's a plane graph, meaning it has no crossings. So what we want to show is that the Delaunay graph has no crossings. We can prove this by contradiction. So let's assume it has a crossing. Then there are 4 vertices, 4 points, that somehow there's an edge between these 2 points, there's an edge between those 2 points, and those 2 edges cross. So if the 4 points look like this, and what I mean by this is I have 3 points on the convex hull and 1 point inside, even if I take the complete graph, there is no crossing. So this is not how these 4 points may look like. They will look like that in the sense that the 4 points form a convex shape or are on their convex hull. And now in this example, okay, we see there is one edge. And from that one edge, we can also conclude there's a joint boundary here. I can also go from that joint boundary in the cell of this point to that point. I'm remaining in that cell. I can also go to infinity here while remaining in that cell. Likewise on the other side. So I can split the plane into 2 halves such that this point is on the one side, this point is on the other side, and at the splitting line, I stay within these 2 cells. Of course, if I have an edge between these 2, the same will be true. I can split again, but what about the joint point here? For one, it has to be in one of those 2 or on their boundary, or on one of those 2 or on their boundary. The only way this can happen is that I actually have a shared vertex here. But in terms of adjacencies and in terms of the definition of the Delaunay graph, I will not count these as being adjacent. So the Delaunay graph will in this case look like this. That's why I'm so far also talking about a Delaunay graph and not a Delaunay triangulation, because a Delaunay triangulation then should have triangles. So a Delaunay triangulation is what I get when I take the Delaunay graph and add edges until I have a triangulation like this, for instance. This is a fairly special situation, I can already say. I mean, we have this degree 4 Voronoi vertex, which actually means that all of these 4 points will be on one circle. So you already see that's a kind of a non-general position situation. In these other examples that we've seen here, and here, we actually already have a triangulation. And that's why we typically simply speak of a Delaunay triangulation. But to introduce a concept, and because, of course, in non-general positions this could happen, we also talk about Delaunay graphs. So far, so good. Now, let's look at a characterization of Delaunay triangles or faces of the Delaunay graph and Delaunay edges, so edges of the Delaunay graph. And for that, we first look at a characterization of Voronoi vertices and Voronoi edges. And for that, we use this circle CP of Q. So what is that? I pick a point Q and I take the largest disk with center Q such that there is no point in the interior. So in this case, it would look something like that. So if I now increase the radius further, it will include this point. but so far it does have no point in the interior. Now we can characterize Voronoi vertices using this disk, namely in the following way. I have that something is a Voronoi vertex exactly if the largest ball with no point in the interior actually has 3 points of P on the boundary. So 1, 2, 3. This is now a vertex. And why is that the case? Because for a Voronoi vertex, it's on the boundary of at least 3 cells, meaning it has 3 nearest neighbors at least, and all of these 3 will be on this disk. For a Voronoi edge, I have 2 nearest neighbors. So what does that mean? It means that this point is on the Voronoi edge of these 2 exactly if these 2 points are the nearest neighbors, meaning if I take the largest empty circle around that point with possibly points or with points on the boundary, then those 2 points will show up on the boundary. So this is a characterization of Voronoi vertices, 3 points on the boundary, and Voronoi edges, like this circle CP has 2 points on the boundary. So this is a statement about Voronoi diagrams, but we're making the statement right now to characterize Delaunay edges and Delaunay triangles or faces of the Delaunay triangulation. Because what does this mean? We will have a face in the Delaunay graph here surrounded by these 3 edges, and we can characterize this face by having an empty circumcircle through the vertices of that face. Yeah, so I have a point set P, and now I can say 3 points are vertices of the same face of the Delaunay graph if and only if I draw the circumcircle through those 3 points, it contains no other point in the interior of the point set. Likewise, something is an edge of the Delaunay triangulation, okay, if and only if the CP for that Voronoi edge is empty, which stated differently simply says if and only if there is an empty circle with those 2 points on the boundary, this is actually a Delaunay edge. So now we have characterized faces in the Delaunay triangulations, in particular in a Delaunay triangulation, the triangles, and Delaunay edges. If we have a triangulation, a triangulation is a Delaunay triangulation if and only if for every triangle I can look at the circumcircle and there's no point inside. So now we know more about the structure of Delaunay triangulations, also how to recognize Delaunay triangulations, because we can simply look at these circumcircles. Let's briefly talk about complexity. So how many triangles does a Delaunay triangulation of n points have at most? And the options are roughly 2n divided by 3, or roughly 2n, or 3n. The correct answer is 2n minus 5, and the easy way to see this is that we're looking at triangles, and those correspond. So let's first look at the setting of general positions. Those correspond to Voronoi vertices, and for Voronoi vertices we already had this pound of 2n minus 5. But we can also derive this again simply with Euler's formula. Next, we're going to take a different perspective on the Delaunay triangulations, or actually we're going to look at triangulations with a different property and see that this will eventually lead us again to Delaunay triangulations. Next, I'd like to talk about triangulations more generally, and specifically about angle optimal triangulations. So let's first start with what is a triangulation of a point set. So a triangulation is defined as being a maximal planar subdivision of that set of points. So what does that mean? So it's a planar subdivision, so it's non-crossing, and I'm using straight line segments as to connect vertices. And it's maximal in the sense that I'm adding as many edges as possible, and in that way every face will be a triangle. So the observations here are, for one, any inner face is a triangle, so any face that I look at here, that's a triangle. Then there's also the outside, so there's the outer face, and the outer face is simply the opposite of the convex hull. So here, this is a convex hull. Everything within the convex hull will be triangulated, and then there's the outside. Now I would like to make a statement about the complexity of a triangulation, and this I will phrase in terms of the number of vertices on the convex hull and n. And let's say n are non-collinear points, so they're not all on the same line. And then I would like to say something about the number of triangles and the number of edges. So maybe that's something you can do on with pen and paper. Keep in mind, useful formula for this might be Euler's formula, which says for a connected plane graph, and this graph is connected because it's maximal, number of faces minus number of edges plus number of vertices is 2, and here we are also counting the outer face. So if you did the computation, you hopefully ended up with the following numbers. We have 2n minus 2 minus h triangles. So if we have a very small convex hull, the smallest convex hull that we could have is 3 points, then we have 2n minus 5 triangles, and if the convex hull is more complex, we have even fewer triangles. And we have 3n minus 3 minus h edges, so we have at most 3n minus 6 edges, and if the convex hull is more complex, fewer ones. Now, given a point set, there's of course many ways to triangulate them. So instead of this edge, I could have used this edge, and so on. So how do we decide which triangulation we actually would like to have? For this, we go back to the motivation of spatial interpolation. So here we had height measurements, we projected them down to the plane. A simple way to get interpolations was using the Voronoi diagram. This is not what we want to do now, but what we want to do now is we want to use a triangulation of the point set, and in that way get continuous heights in the plane. And the question that we're asking is, what is a good triangulation? Let's have a look at an example of a point set. So here we have the same point set in both drawings, but different triangulations. So where do they differ? They differ in exactly this edge, here and here. Now, which one is better? That, of course, depends on what actually happens in that phase, and we don't know. But let's make a best guess. So we're looking at, let's say, the same point here and there. So if you look at those 2 points, then on the left-hand side, we're going to interpolate between those two, and we will get a height of, let's say, 985. Here we will interpolate between those two and get a much smaller height. Now, of course, we don't know which one is true, but it seems more natural to go with the values that are closer to that point. And so in this terrain here, we have this ridge that goes through, and we have measurements fairly closely along that ridge. Here, now there's this sudden drop and it goes up again. Could be true, but seems unlikely. And what we don't like about this specific triangulation is that this point gets values from points very far away, which is of course relative, but it means also one way of interpreting it is that we have a very long triangle. So let's say skinny triangle or thin triangle. So we would like to avoid those. And thin triangles come from having small angles. So what we would like to do is to avoid small angles. And as an optimization criterion, what we could say is, and what we will say now is, we want to maximize the smallest angle within the triangles. And this will then be angle optimal triangulations. So given a triangulation, we will look at the so-called angle vector. And the angle vector will simply list all angles sorted by increasing values. Okay, so this is not the most exciting angle vector because all angles are 60 degrees. This one is more interesting. Here we have some with 30 degrees, 4, and then 2 with 120 degrees. And now we're going to compare triangulations based on lexicographical ordering. So what we're saying is we're going to look at the smallest angle, in this case 60 and 30, and then sort them based on that value. So this one will be higher in the order because it has a higher value here. If they would have both had a 60 here, we would have looked at the next one and the next one and the next one and so on. So that means that we're doing lexicographical ordering. In terms of angle optimality and avoiding small angles, we would now want to say that this one is not so good. So we're going to take the triangulation that is maximal with regard to this ordering. So we say a triangulation is angle optimal if its angle vector is larger or equal to any other angle vector of any other triangulation. So now we want to find angle optimal triangulations, and we were going to see a very simple algorithm to get them. And for that, we're going to introduce the concept of edge flips. So here we again have a triangulation. And now we're going to say that this edge is illegal because if I take out this edge and replace it by the opposite edge, then the angle vector improves. Yeah, so this edge is illegal if the smallest angle incident to that edge, if I can increase that by flipping the edge. So here the smallest angle is 30 degrees, and flipping gives me instead these angles here, which are 60 degrees. So this edge would be illegal. If I want to have an angle optimal triangulation, I would want to flip that edge. If I flip an illegal edge, it also means that the angle vector, so after flipping here, the angle vector will have improved or will have increased in terms of the lexicographical order. Okay, so let's look at this by an example. If I want to remove all illegal edges in this example, how many flips do I need? 0, 2, or 3? Here I need 3 flips. You might have answered 2 because you see 2 illegal edges, and that is actually correct. There are 2 illegal edges. So why do I say that I need 3 flips? So now I flipped one of the edges. Let me flip the other edge. After flipping that edge, this edge becomes illegal. So I also have to flip that one. And then after 3 flips, I'm done. So here we needed 3 flips to remove all illegal edges. So what we're going to look at next is how can we check whether an edge is illegal without explicitly comparing angles. We've seen illegal edges and characterize them by angles. So now we want to take a different perspective on illegal edges, and this will bring this concept of illegal edges and then legal triangulations back to the concept of Delaunay triangulations. So for that we start with Thales' theorem, which is a statement about angles and relates it to circles. Specifically, you will have seen it in the following form. So if I have A and B, and they kind of are on the diameter or the diameter of a circle, and now I have a third point C. Now on the circle, then this is a right angle. So no matter which point I pick here. So this you will know from high school most likely. I will want to show you a generalization of this theorem, and it is the following. So instead of taking a line segment that is a diameter, I'm taking arbitrary points A and B on the circle. They form this segment here. Now, of course, if I take a third point, this is not necessarily a 90-degree angle. But the generalization that I'm using here states the following. If I have 2 points on the circle, P and Q, and I'm looking at the angle at P here and the angle of Q for Q here, those 2 angles will be the same no matter where these points lie on the circle. Furthermore, if I take a point inside the circle, like R here, this angle here will be bigger than those 2 angles. And if I take one outside, like S, this angle here will be smaller. We can use Thales' theorem to characterize whether an edge is illegal or not in the following way. So let's say I want to know whether PQ here is illegal. And for that, I look at the 2 incident triangles, so PRQ and PQS. This gives me these points R and S. And PQ is illegal if and only if I take the circumcircle through one of those 2 triangles. So let's say through P, R, and Q, so the circle that goes through those 3 points. And I look at where S lies. If S lies in the circle, the edge is illegal. If it lies outside, so if S would be here, it would be legal. So how can we prove that? We're using Thales' theorem. So essentially any angle that is in this triangulation currently, I will want to set into a relation with an angle that I would get if I take that triangulation. For instance, if you take this angle here, now it's the angle of, we're taking this here as a base of this point on that circle with that edge as a base. I can set that in relation to this angle here, which is larger because S is inside the circle. So by Thales' theorem, this is larger, and I can do this for all of the angles. And by going through all of these calculations, I see that indeed my edge was illegal or is illegal if and only if S is inside. And this gives me a way to see whether an edge is illegal without measuring angles. So for instance, this edge here, I can ask, is it illegal? So for that, I draw the circumcircle through 3 of the vertices of an incident triangle. The triangle on the other side, the remaining vertex, that is in that circle, so I know it's illegal. So if I want to get rid of illegal edges, I would now flip it and would have improved my triangulation. In this example here, we have no illegal edges left, and this we now call a legal triangulation. First natural question would be to ask, okay, I've defined this concept of legal triangulations, but do they actually exist? Can I always construct a legal triangulation? The answer to this is yes. So here's a very simple algorithm, and it's not necessarily efficient, but it will lead to a legal triangulation. So what it does, whenever there's still an illegal edge, I will flip it. So why might this not lead to a legal triangulation? It might not lead to a legal triangulation if I somehow have an infinite loop. But this cannot happen because we know that with every flip, the angle vector strictly improves. So if the angle vector strictly increases, I will have to, every time I do a flip, be at a triangulation that I haven't seen so far. And because the number of triangulations on a point set is finite, this will mean that at some point this algorithm will finish. Let's look at the relation between legal triangulations and angle optimal triangulations. I mean, that was our motivation, to look at illegal edges and making triangulations legal. So of course, any angle optimal triangulation is legal. So an angle optimization is maximum in relation to the angle vector. So there's no flip that could improve it. So angle optimal triangulations are legal. But is every legal triangulation also angle optimal? We will see that, at least in general position, this actually then is a case. And we'll see this through looking at Delaunay triangulations. What we have, namely, is that if I have a set of points, a triangulation is legal if and only if it is a Delaunay triangulation. So what is the relationship between legal triangulations and Delaunay triangulations? So let's look at this configuration here. This is not legal, and it is not legal, so the edge PR is not legal because I have this incident triangle and its vertex is inside the circle. So for the Delaunay triangulations, we had a similar but stronger criterion. There we said, okay, this cannot be a Delaunay triangle because the circumcircle should be completely empty. So not only this point shouldn't be here, but also any other point shouldn't be. So this is all forbidden for Delaunay triangulation. Being Delaunay, or for an edge then to be Delaunay, so meaning that I should be able to find an empty circumcircle, is a stronger statement as such than being legal. That also means, in terms of the proof, the one direction is straightforward. If a triangle is a Delaunay triangle, in particular means the circumcircle is empty. It means that also the point S cannot be in that circumcircle. The other direction is a bit more work. Let's assume I have this point S in the interior, but I do not have this triangle. What I want to prove is that also for legal triangulations, there cannot be a point here in this circumcircle. If it's a neighboring point, so if I have these edges, then obviously it's not legal and I'm fine. The problematic case is if there's something in between. Yeah, so could I have a setting like that? The neighboring one is outside, but now there's a different one that is inside. So the proof that this cannot happen will be proved by contradiction. So suppose we have such a point, and we're going to pick this setting such that this is a PQR is a triangle with a property that the angle here at S is maximized. So it's a triangle with S in the circumcircle with maximal angle here. But what we get now is that we assume that T is now the third point of the triangle with P and R. So the circumcircle of that one lies slightly above that other circumcircle. So center moves along that center line here slightly. So it is further up here. And that in particular means that S is also inside of this one. And if I take now this angle, it is this angle plus that angle. So in that angle, okay, I need to show that that is a positive angle, but I can use Thales theorem to observe that. So I know this angle is even bigger, contradicting our initial assumption of how we picked this triangle. In conclusion, this cannot happen. And in conclusion, this means that a triangulation is legal if and only if it's a Delaunay triangulation. Now, if we have points in general position, there's exactly one Delaunay triangulation for a point set. So it is unique. That also means the legal triangulation for such a point set is unique. Now we know that the angle optimal triangulation is legal. If there's only one legal triangulation, then I know that that legal triangulation is also angle optimal. That means that in this setting of general position, angle optimal, legal, and Delaunay are all the same thing. In particular, meaning that the Delaunay triangulation in this setting is angle optimal. And more generally, also in non-general position, the angle optimal triangulation will be legal. A legal triangulation will be a Delaunay triangulation, meaning that one of the Delaunay triangulations of the Delaunay graph, if we now are not speaking about general position, will be the angle optimal triangulation or an angle optimal triangulation. Natural question is, if I'm in non-general position, is then every Delaunay triangulation still angle optimal? Options are yes, but the proof is more complicated. No, but still the smallest angle is maximized, or no, and not even the smallest angle is optimized. The correct answer is no, but the smallest angle is still maximized. And again, we can prove this by Thales theorem that the smallest angle is maximized, but indeed not every Delaunay triangulation in non-general position will be angle optimal. But the case we're most interested in is general position and then legal Delaunay angle optimal, all the same. Next, we want to look at how to compute Delaunay triangulation. We want to compute the Delaunay triangulation, and we want to do so using a randomized incremental construction. So how will this look like? What we're going to compute will look like that. So we will have our point set, but because we will want to have a big outer face, we will add 3 points on the outside. So this is what we're going to compute, and we're going to do it in the following way. We initially create a large outer triangle, then we randomly permute our points because we wanted to use a randomized incremental construction. We add them one by one. So for each point, we insert it into the current triangulation, making sure that we again have a Delaunay triangulation, and at the very end, we discard the outer points, and what remains will be the Delaunay triangulation of our point set. So when we insert a point, so here, when we insert a point, what do we need to do? So first of all, we need to find the triangle that contains this point. And we have to discuss how to do that later. If I know that triangle, I can do the following. I split that triangle by placing this point here and adding those edges. Now I have 3 triangles. Now, this might not be the Delaunay triangulation. So how can we make sure that we get a Delaunay triangulation? So here's a very simple way of doing so, and we still need to prove that that is actually correct. Namely the following. So we do this, and now we check for the opposing edges, so these 3 edges, we check whether they are legal. And for this we have this recursive method, LegalizeEdge, that we will call 3 times, once for each edge. So legalizing this edge will check whether this edge is legal. If it is not, if it's legal, we're done. If it's not legal, I would remove it. So I would flip, and then I would have to check those two edges. So that's the idea here. Okay, that is if the point lies within a triangle. There is a special case if it lies on an edge, then we would kind of split it like that into triangles. So this will be the case we're going to focus on. The other case is essentially the same. So once more, how do I now legalize an edge? So this is, let's say, my new point. If I call legalize on that edge, I know how to check that. I can check whether the point on the other side, so forming this triangle, whether that point is in the circumcircle of these three. If it's inside, the edge is illegal. If the edge is illegal, I want to flip it. So I will flip this edge, getting rid of that one. Now, possibly, these two edges are illegal. So I will recursively call LegalizeEdge on those two edges. We need to check whether all edges that we get in this way, or all edges in the triangulation that we then have, are actually Delaunay. So that is what we need to prove to show that this is correct. So all edges that we inserted, those are legal. And how can we see that? So let's say this is our new point. All edges that we inserted are actually incident to that point. So they have this as a vertex. And locally that looks like this. So here's my new point. Previously I had this edge here, and the circumcircle of PJ, PL and PI previously was empty, but now PR was added, so my new point. Can I find an empty circle for this edge? And that is indeed the case. I can start from this circumcircle of the three old points and shrink it inside in the direction of PL until it includes PR. And in this way I get a circle that is completely within this old circumcircle that was empty. So it is again empty, and the edge is Delaunay. Now all edges on the boundary of this region, I checked whether they're legal, and I mean the algorithm stopped because they were legal, so they are legal. All edges outside are also legal because for them nothing changed, and legal is a local criterion. So now we know all edges are legal, therefore we know legal or Delaunay, but that is the same thing. So all edges are in particular Delaunay edges. What remains now is to see how do I actually find which triangle to insert into, and we're going to see that next. We are in the midst of computing the Delaunay triangulation using a randomized incremental construction. We've seen how to update the Delaunay triangulation when I have a point and I know which triangle, old triangle it falls into. What we haven't talked about yet is A, how do we actually kind of initialize this big triangle at the beginning? B, how do we actually find the triangle that contains a new point? And for that we are going to need a search structure. So let's start with this big triangle outside. So we're going to have points P0, P-1, P-2, which somehow should be far enough away so that they don't interact with the triangulation, with the Delaunay triangulation of the point set. The best way or safest way of doing so is to treat these points outside symbolically. So we're not actually giving them locations. We're just making sure that anytime we do a test, like a test of is this point within the circumcircle of some triangle, we're going to treat this point as being very far away. So these points will not be in circumcircles. So that's the initialization. What this gives us is that at the very beginning, when we start our construction, we have a big triangle outside. So when I insert my first point, I know it will be in that triangle. And now we're going to use a search structure that kind of starts, so if I get a new point, I start with a big triangle. And within that big triangle, I will fall into smaller triangles. And in that way, I can find my way eventually to the triangle that contains the point. So how does this look like more specifically? We're going to build a search structure where the leaves correspond to the current triangle, so the triangles currently in the Delaunay triangulation, and the inner nodes corresponds to triangles that have been deleted. So they were there somewhere in the construction, but they were deleted. For instance, here I have my current triangulation, and then I have these leaves, delta 1, delta 2, delta 3 for the current triangles. if I'm now inserting a new point, let's say this point PR, what does it mean? I'm deleting the triangle delta 1 first. I'm splitting it into 3 parts, meaning I will get 3 new triangles here, which attach to the triangle that I just deleted. So now if I have a point that lies, let's say here, I will first see it's in the big triangle. At some point I will work my way to figuring out that it's in delta 1. And then when I know that it's in delta 1, I will have to check which of the 3 children contains that point, and then I can go further down that structure. Now in this example, I get those 3 triangles, but I would still, let's say, legalize this edge here, meaning I would have this flip here. This means that this triangle up here and delta 2, those are replaced by 2 other triangles, delta 4 and delta 5. How do we achieve this? So this triangle here corresponds to that one, and I have delta 2. Those 2 will be deleted, and they together cover delta 4 and delta 5, so I have pointers from those 2 triangles to delta 4 and delta 5. And then let's say I have another flip, namely these 2 triangles disappear and are replaced by those 2. Then I would take delta 4, and this down here is delta 3, delta 4 and delta 3. They would now be inner triangles with delta 6 and delta 7 as children. In this way I build the structure, and then if I have a query, it first falls into the big triangle, outer triangle, and then this structure will always tell me, okay, I have a triangle, it has some children, so I test which child I'm in, and these are either 3 children in this case or 2 children in that case. And in that way I can eventually find the triangle that I'm currently contained. So that's how I search, and that's how the search structure looks like. Now we want to show something about the complexity of our algorithm. Specifically, we want to show that the triangles that we create during the process, that we only have a linear number of those triangles. In particular, this means that the search structure will have linear size. So what I want to show is that the expected number of triangles created in the whole process is at most 9n plus 1, so it's linear. For this, we use backwards analysis. So we have a given triangulation. Any point in that triangulation has the same probability of being the last one, and we ask how many triangles were inserted if a certain point, let's say PR, was the last one. Each of these points now has the same probability, 1 divided if it's the rth point, or 1 divided by r of being the last point. So I can say something about the expected degree of the last point, because I can say something about the overall degree. We have that the overall number of edges is bounded by 3n for n points, or 3r for r points. The degree is the sum of degrees that is at most 2 times this. So if I sum up all the degrees, that's bounded by 6r, and then if I take the average degree, so the expected degree of the last point is bounded by 6. So what does that tell me about how many triangles were created? So if something, let's say something has a degree of 6. So this is my last point, and it has a degree of 6. 1, 2, 3, 5, 6. So what happened during the insertion of that point? So initially, let's say it ended up in a triangle. I created 3 triangles. That's already a 3. Now for every other edge that this vertex has afterwards, I needed 1 flip. So with 1 flip, I would have had this situation. This increases the degree by 1, but it creates 2 new triangles. So meaning I get here plus 2. Now this gives me degree 4. I have another flip, which, it also deletes some triangles, but it creates 2 new ones, so plus 2. Now I have a degree of 5, and 1 more plus 2 would give me, in this case, a degree of 6. More generally speaking, the number of triangles created if I insert a point of a certain degree is the following: 2 times that degree, because for every edge that I want to have, I pay 2, except for the first 3 edges, because they kind of came for free, because I just, not for free, I created 3 triangles when I first inserted. So the number of triangles created can be bounded by 2 times degree minus 3. The expected degree is 6, so the expected number of triangles created is bounded by 2 times 6. So that's 12 minus 3, that's 9. And I have the outer triangle, so that gives me one more. So overall, I get this bound of 9n plus 1 on the expected number of triangles created during the construction. So that's the update cost. So if I now want to completely analyze the algorithm, I also need to analyze how long searching takes. So this gives me A, how big is the search structure, and B, also how much time it took to legalize all those edges. But what I haven't accounted for yet is how long does it take me to find my points in the search structure. The proof or the analysis you can find in the book. It's slightly more intricate, and I'm going to leave it out here, but what you get, that overall your construction will run in expected order n log n time. So what we know now is we can compute the Delaunay triangulation of n points in expected order n log n time using a randomized incremental construction. We now never actually talked about how to compute Voronoi diagrams. So how fast can we actually compute a Voronoi diagram? In linear time, or also in order n log n time? Or do we for that actually need quadratic time? We can also compute Voronoi diagrams in expected n log n time, namely simply for the reason that the Delaunay triangulation contains already all the information we need to construct the Voronoi diagram. So from the Delaunay triangulation, I can in linear time go to the Voronoi diagram, and in that way also get that in expected order n log n time. Now I always have to say expected because we saw a randomized incremental construction. Both the Delaunay triangulation and the Voronoi diagram can also be computed deterministically in order n log n time. So to sum things up, we've seen how to compute Delaunay triangulations, and as that also know how to compute Voronoi diagrams in order n log n time using a randomized incremental construction.